Lauren? Uh-huh. Okay. So one side went up. And what happened when you plugged in 0? What was 2 to the 0 power? Okay, so we had 1. Sorry, my thing is not aligned very well today. Okay, and we had something that looked like this, and this got closer and closer to 0 here. Okay, fair enough? All right, so what about when you went and graphed y equals 5 to the x? How did that compare to the graph of y equals 2 to the x? Sean? Good. Okay, so same shape. Like if you look from far away, right? Same general shape, but he's right. It's a lot steeper. Instead of, you had the point still, when you plugged in 0, you still got 1, right? But now when you plugged in 1, instead of getting 2, you got 5, right? And then you would have got 25, which was off the charts. So this was a lot steeper. Okay. But general shape was the same, right? Getting closer to 0 over here and growing over here. But growing faster because of the base of 5 instead of 2. Okay. All right, what about when you graphed y equals 1/2 to the power of x? Yeah, Alvin? Okay, it was the same graph but reversed. Kind of reflected which direction, vertically or horizontally? Horizontally, right? Okay, like left to right and right to left. What still happened when you plugged in 0? You still got 1, right? So you still got this point at 0, 1. Oh, that's interesting. Okay. And the graph goes, well, that's not accurate. I know it'll be close to that after that. Okay, something like this. Okay. So here, when x got bigger, what happened to the value of y? It got smaller, right? And we kind of investigated that before when we looked at ratios less than 1 and what happens when we raise them to big powers, okay? But then as x got smaller, what happened to this value? It actually got bigger, right? Because what do negative exponents do? They flip it and use the reciprocal. So the reciprocal of 1/2 is 2. So when you're using a negative exponent, you're actually raising 2 to a power instead of 1/2, which is why it's growing so much on that side. Okay? All right, what happened when you did y equals 2/3 to the power of x? Same thing, okay? So you still have 0, 1. When you plugged in 1, you didn't get 1/2, you got 2/3, so it's a little higher here. And when you plugged in -1, you didn't get 2, you got like 1.5. Okay. So something like this. The same general shape and the same sort of reference point. In all these shapes that you guys drew, you said they got closer and closer to 0. Did they ever hit 0? No. So do you think there are any asymptotes on this graph? Vertical or horizontal? Horizontal. And what would be the horizontal asymptote for all 4 of these graphs? So you guys said horizontal. Horizontal lines have the equation y equals 0, right? Because every point on this line would have the same y coordinate, but not the same x coordinate. Okay, so that's why it's y equals gives you a horizontal line. Okay. So we're going to summarize and graph a parent, and then you guys will be able to do the notes tonight. You're going to need to remember your transformations for the notes tonight. And the different thing about exponential functions is there isn't one parent function. There's lots of parent functions, right? Because did y equals 2 to the x look exactly like y equals 5 to the x? Same general shape, some properties that were the same, but 5 to the x was steeper, right? So when we have exponential growth, we're going to have this exponential equation. For it to be growth, what has to be true about the base of the exponential function? So look at back at your graphs. The first 2 were growth, and the second 2 were decay. Jordan? It doesn't have to be a whole number. I know I kind of made it seem like that with the examples that I put on there. Ben? Has to be greater than 1, okay? So here, for exponential growth, your base will be bigger than 1. Okay? And those graphs will always have the shape that you saw for y equals 2 to the x and y equals 5 to the x, meaning they'll always be getting closer and closer to 0 over here, and they'll go up like this. Okay? The graphs all have some same characteristics even when we change the base number. They all had this point right here that was at the point, 0, 1, and they all had this asymptote at y equals 0. The points around this are going to vary depending on your base. Okay, so each of these functions has a new parent function. If you want to graph something that looks like y equals 2 to the x minus 5 plus 1, oh, I want to put a negative in front of there. Okay, that's a horizontal shift to the right 5, a vertical shift up 1, and a vertical reflection, just like we've done before. But to know the parent function of this, I would have to graph 2 to the x. If someone changed this to a 4, the graph would generally still have the same shape, the transformations would be the same, but the parent function would be slightly different with a 4 here than with a 2 here. Does that make sense to everybody? So that's a little different than what we've done before. Okay? All right, so exponential decay, the formula or equation looks the same. It's still a base raised to a power. But what's true about the base in the function if we're going to have it be decay? Jonah?
Base must be less than 1 or greater than 0.
Good. Greater than 0, but less than 1. Oh, I didn't write it right. I'm having issues today. Greater than 0, but less than 1. Okay. Now, notice that we didn't consider anything where b is negative. We did with sequences and series, right? That the ratio could be negative. But with an exponential graph, if the base was negative, would your graph keep this nice curved shape? No, because a negative power raised to, or a negative number raised to an odd power would be like a negative number. But then when it got raised to an even number, it would be a positive number, and then it'd be a negative number, and then it'd be a positive number. So we don't study them in this graphical function. They can still converge and diverge like we talked about before, but graphing, they don't follow these same procedures. Okay? So what's the difference when I change the base to be something that's decay between 0 and 1 compared to when I did growth? How is the graph going to look different? Michelle? Uh-huh. Good. So instead of going upward over here, it actually goes more like this, right? But the exponential growth and decay graphs still have some things in common. What does the exponential decay graph have that the exponential growth graph has also? Okay, an asymptote right here at y equals 0. Good. And what else? Michelle?
They have one y intercept, and also when they go to the right, the y flips.
Okay, gotcha. Yeah, especially if the bases are reciprocals of each other. Okay. So they both have one y-intercept, and specifically, what is the intercept? If we're not doing any transformations, we're just taking a number to a power, and you plug in 0 for the power. Savannah? It's going to be 0, 1 all the time. So every parent function is going to have that. Can that change if I do some transformations? If I stretch it, compress it, shift it? Yes. Okay? Now, things are going to get a little bit different in these graphs when you watch the examples at home, because if you're going to stretch and compress this, if you stretch and compress it vertically, the asymptote stays. The only thing that moves the asymptote is moving it up or down, right? Left or right is not going to do anything to that, okay? Stretching and compressing doesn't do anything to the asymptote, but all the points will move further away from the asymptote if they're vertically stretched, or all of them will move closer to the asymptote if they're vertically compressed. But what if we wanted to do horizontal stretches and compressions? Can I measure how far that point is horizontally from the asymptote? Here's the asymptote. Can you measure a horizontal distance from that point to the asymptote? So can you move left or right only and reach the asymptote and know some distance from this point? No. Okay, it can't be measured from the asymptote. Okay? So what do you guys think we're going to do when we stretch and compress horizontally? What do you think is going to stay in the place and things are going to get compressed towards that or stretched away from it? Yeah? The y-axis if you haven't shifted at all. So basically this y-intercept point, okay? And it talks a little bit in the video about y. If you guys have a stretch or compression, right, then that means there's a number here in front of x that's maybe stretching or compressing it. When I plug 0 in for x, does that 2 have any effect on the 0? No, so it's still like a 0. So that's why that guy doesn't change when you horizontally stretch it and compress it, okay? All right, so we'll graph one function with an actual base. So each of the problems you get in the notes tonight are going to have stretches, compressions, shifting. They're going to have some transformations. So what you're going to see in the notes is you're going to see us first graph the parent function, then remember what the transformations are, and then do those transformations to get the final graph. Okay? So we're going to do this one together just so that you guys understand where the parent function is coming from. So this one is just a parent function, right? It has no stretches, compressions, reflections, or shifting. It's just a base to the power of x. Okay? Is this parent function an example of exponential growth or exponential decay? Growth, right? Because my base is bigger than 1. So I expect my outcome to look like this, okay, compared to this. Okay. Since there's no shifting up and down, I still expect this asymptote to stay at y equals 0. And since there's no shifting left, right, up, down, stretches, compressions, things like that, I know that every parent function, which this would be a parent function, has this point at 0, 1. Okay? So I'm going to go ahead and fill those things in for myself. I know I have an asymptote here at y equals 0. I know I have the point 0, 1. Now here's where the parent functions are all different from each other depending on the base. To get a point on each side of that 0, 1 point, you have to actually evaluate this to some power. Okay? So 3.1 to the first power. If I plug in 1 for x, I would get 3.1 for y. So I have the point 1, 3.1. What happens if I plug in negative 1 for x? How am I going to try to calculate 3.1 to the negative 1 power? Lauren? Yeah, so essentially I'm going to think of it 3.1 to the negative 1 power as 1 over 3.1. I don't know exactly what that is, but it's really close to being 1/3, right? Okay, so that's kind of where I'm going to plot it around. So for negative 1, I get something like 1/3, and then I can see the general shape that I was expecting for my graph. So that's how we're getting each of the parent functions. So in the future examples, you're going to see that part graphed right here because that's not the final answer. And then we'll do stretching and compressing and stuff to get it over there. Okay? Are we good with exponential growth versus decay, the basic parts of the graph so we can get the parent ones? And you'll watch the video for the stretching, compressing, and get those examples from there. Okay? All right. We're good.